Hey, so good afternoon. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, for those of you that don't know me. And this afternoon, it's a great pleasure to welcome Professor Vishnu Jejjala, who came the long way from Wits. Yeah? So welcome to the Western Cape and to Stellenbosch. Vishnu started his scientific career as a paleontologist. Yeah? But then when he was 7, he decided maybe astronomy is the thing. Yeah? Yeah? And so he became a theoretical physicist. He did his PhD in physics at the University of Illinois in Urbana-Champaign in 2002. And after several postdoctoral positions across continents, he ended up as a South African researcher in theoretical particle cosmology at Wits, where he is still today, and he's also a professor in the physics department at Wits. Yeah? And today it looks like he not only has a passion for cosmology and particle physics, but also for AI. AI. So maybe we will hear how this transition comes about, yeah, from particle physics to AI or the other way around. I'm not so sure. Yeah. So Vishnu, thank you very much for coming, and we are looking forward to your talk. I think everything is set up.
Great. Thanks for my presentation. I'd like to tell you about some work I've been doing lately. Mathematics, theoretical physics, and artificial intelligence. So the talk is largely about topology. Topology is about shapes. Topology is also about functions between shapes. So two shapes are topologically equivalent in that you can from each other without doing some unequal operations. So you can bend, you can twist, you can stretch, you can crumple, but you can't pair. You can't go in different parts of your space together. So you can express topology as equivalence in terms of homomorphism in between spaces. But all of us have a more or less correct intuitive understanding of topology. So, for example, the soccer ball and the donut are different things because they have a different number of holes. And you can't really form one in the other without doing these unequal operations. So we have this notion of topology is sort of intrinsic how we think about spaces. So we encountered topology as kids when we discussed platonic solids in elementary school, maybe. So platonic solids are these convex regular polyhedra in 3 dimensions, and there are 5 of these, famously. They teach us prove there are exactly 5 of these, and apocryphally we discovered the octahedron and the icosahedron. This was a friend of Plato, hence the name Platonic solids, and one of the great Platonic dialogues is named after him. It's essentially the theory of epistemology at its foundational level. So these Platonic solids are examples of objects we encounter, and they're characterized by property that the ordered characteristic of all of these objects is the same. So you take the number of vertices in these objects, the number of edges, the number of faces. You take the vertices, you subtract the edges, you add the faces, you always get 2. So I've listed the E's, the F's, all these solids, but it turns out this is true even if it's not a platonic solid. So take a prism, for example, and you find the same formula, E minus E plus F equals 2. And this was noticed by Moralico for the platonic solids. Moralico is a famous mathematician. He discovered the method of proof by induction. So he's famous for that, but he's also the one who's credited with noticing that these Euler characteristic is the same for all of these solids. But Euler extended this work and publicized this far more than Moralico did, and hence his name is attached to it. Usually in mathematics, or often in mathematics, the guy who discovered something is not the guy it's named after. This is maybe a moral lesson. I don't know. So these Euler characteristic also translates to another topological property, the genus. The genus is essentially a number of holes. And if you relate the 2 minus 2 times the number of holes, you get the Euler characteristic for these objects. So all of these platonic solids, for example, can be mapped to spheres. The sphere's got no holes in it, so they're genus 0 objects. So 2 minus 2g equals 2 means that g equals 0. So that's the topological invariant you associate to a sphere. Similarly, a coffee mug or a donut has 1 hole in it.
So the other characteristic here is 0, meaning the genus is 1. So the figure here illustrates how you can continuously deform a coffee mug into a donut. So topologically, they're the same thing. Okay, so we're interested in these topological objects. So a topologist's morning may consist of a cup of coffee, putting on a pair of trousers, and putting on a shirt. So an object with 1 hole, an object with 2 holes, an object with 3 holes. We encounter topology in physics quite often. So one of the fundamental laws of electromagnetism is Gauss's law. And we typically think about a charge, we surround it with a sphere. But it needn't be a sphere. It could be any object which surrounds that charge. So the shape of the object doesn't matter. All that matters is that there are no holes in this object. So all the flux lines that emanate from a charge, all these electrical field lines, they pass through this object that envelops that charge. Similarly, Ampere's law, we're interested in this loop which goes around a current, but the loop can have any shape you want. So the important thing is that the current passes through this loop. It doesn't matter what the shape is. So we're already familiar in physics with this notion of topology, and a lot of the things we calculate really are independent of the shape of the thing that we're studying. In quantum mechanics, there's this famous Aharonov-Bohm effect in which we consider the wave function of a particle in quantum mechanics, and this is sensitive to the amount of flux through, say, a solenoid. So even though the particle doesn't experience a magnetic field, say, it's still aware of the fact there's a potential associated to this magnetic field, and this consequence in physics is called flux quantization. In order for the wave function to be well defined, this object, this flux, which is through this tube, needs to be integer quantized in units of 2 pi. So we encounter in physics this notion of topology that manifests in having, for the wave function to be well defined in this setting, this object has to be integer. So this is because we have e to the I times some phase, and if you add 2 pi to that phase, nothing changes because e to the 2 pi I is famously equal to 1. There are other quantum mechanical systems, for example, the quantum Hall effect, which are sensitive to edge modes, and therefore they're topological in character. They rely on the topology and not the precise geometry. So I want to distinguish between these two things. Topology, which tells us about gross properties of an object, like the number of holes it has, and geometry, which is sensitive to the difference between a coffee mug and a donut. Okay, so I want to come up with examples where topology is really intrinsic to the description of a phenomenon in mathematics or in physics, and I want to see whether I can learn about topology using new tools. So that's the point of this talk, to explain how these things fit together and what we do. So the first case study is knot theory. Knot theory is a beautiful subject in mathematics, but it's also very deeply connected to what we consider to be fundamental physics. So I'll explain how these things are connected, and then I'll explain what we can say about knots using these new tools. Okay, so what's a knot? A knot's a circle embedded in a three-dimensional space. For simplicity, I'll take the three-dimensional space to be a three-sphere. And I've shown you the simplest knots. So the unknot is no knot at all. It's just taking a shoelace and gluing the two edges of the shoelace together. So there's no knot there. Simplest knot is a three-crossing knot. It's called the trefoil. The next simplest knot is a figure-8 knot, has 4 crossings. And if we have 5 crossings, there are 2 different knots we can draw, the cinquefoil and the 3-twist knot. So mathematicians have tabulated these knots. So these are all the knots up to 7 crossings. And then these are knots up to 8 crossings. And these are knots with 9 crossings. And there's a catalog of these knots that mathematicians have compiled over the past century and a half. So for a long time, the late 19th century, people were thinking about the structure of atoms in terms of vortices, describe these vortices in terms of knots. So the original periodic table was a theory of knots. And there's therefore this, physics link from the early days in this study. Okay, so we can draw a knot in many different ways. So for example, if you look at the figure on the left, you can see that it can be untwisted into the unknot. So by crossing number, I mean the minimal crossing number, the minimum number of crossings among the strands of this knot. So the left figure shows more crossings than there really need to be in order to describe the unknot. So there are different moves you can make. They're called Reidemeister moves that are developed in a very precise sort of way that lets us complicate a knot. You can start off with a simple knot and make it look very, very messy. So there's a twist operation which we saw previously, but there's also this operation which pokes or slides these strands across each other. Okay, so applying these Reidemeister moves, you can make a very simple knot look very, very complicated. So both the pictures at the bottom are different versions of this unknot. Just by staring at this, it's very hard for you to do the actual moves in your head to envision these complicated unknots as a simple unknot at top. So you need to come up with a way to describe the properties of a knot that are maybe subtle and may not be obvious by just looking at it. So you can't really count the number of holes the way we did for a donut. We need to be a bit more sophisticated in describing the topology of these objects. So this was actually an issue because the original knot tables that were developed in the late 19th century, they had errors in it. And this particular error, there are these two knots with 10 crossings. They were 10-161 and 10-162 in the database, this Rolfson table. It was only realized in 1973 that by doing these Reidemeister moves, you can convert this guy into this guy. It's not at all obvious, and this error persisted for nearly a century in the tables. So it was a lawyer in New York, Perko, who discovered these knots were the same by finding the right moves to convert one to the other. So it turns out that these questions are very, very subtle, and they're very elusive even to mathematicians. So how do you characterize a knot? Well, you can come up with topological invariants. These topological invariants are the same irrespective of how you draw the knot. Whether you have a complicated unknot or a simple unknot, if you calculate these things, you should get the same answer. That's why we call it an invariant. It's invariant of how you draw the object. So one such invariant is a polynomial invariant. You take a knot and associate to this knot a polynomial, a Laurent polynomial, so it has positive coefficients, so it has positive degrees and negative degrees. And this polynomial is supposed to be a property of the knot, which is independent of how you draw the knot. One such polynomial was developed by this mathematician called Jones, and it's called the Jones polynomial. And it can be calculated in a combinatorial way. I'm not going to go into the details of how to calculate it, but you can do it in a combinatorial way. Now, there's another way to calculate the same object. You can calculate it using quantum field theory. So quantum field theory is our language for expressing physics. So essentially, any fundamental theory of physics is described by this quantum field theory. And these quantum field theories are quantum in that there's an h bar, which explains that there is a scale which is really microscopic, but there's also a structure that you build on top of this this h bar. In particular, we're looking at relativistic quantum field theories. There's also going to be speed of light, which is intrinsic to the game. So given a particular quantum field theory called Chern-Simons theory in 3 dimensions, you can calculate these Jones polynomials. So Witten proposed a way of doing this and came up with a physics identification of this particular invariant of a knot. And in particular, you're calculating what are called vacuum expectation values of certain operators in the theory. Again, the details don't matter very much, but the idea is that this mathematical object, this knot, has associated to it an invariant. This invariant can be calculated combinatorially, but can also be calculated with physics. So there's a physics connection that is underlying this particular invariant of a knot. Okay? All right. So it turns out that there's actually an infinite family of these Jones polynomials, and they're associated to what are called representations of this group SU2. So SU2 is, for people who are familiar with the quantum mechanics, or maybe people who are familiar with quantum information theory these days, this is the group you associate to particles with spin. So if you have a spin 1/2 particle, an electron which can be spin up or spin down, you think about these things in terms of what are called Pauli matrices, these 2x2 matrices that satisfy a certain group algebra. But it turns out that for SU2, these matrices can be whatever size you like. You have 2x2 matrices that satisfy this algebra, you have 3x3 matrices, you have 4x4 matrices, etc. So each of these ways of describing this algebra for this group is called representation. And for each representation, you have what's called a colored Jones polynomial. The ordinary Jones polynomial that you computed combinatorially initially corresponds to the fundamental representation of SU2, these 2x2 matrices. But you can have other representations of SU2, these higher rank matrices. And these higher matrices, they correspond to these colored Jones polynomials. So you have a tower of these topological invariants that you associate to these particular polynomial invariants that you calculate in quantum field theory, you associate to these knots. So we're building these things layer on top of layer. We started off with a knot, then we thought about these invariants, we thought about how to calculate these invariants in physics, and we find that we can calculate more and more such invariants in physics. So we have all of these objects to play with that are topological invariants, and they're independent of how the knot is drawn. No matter how you draw the knot, get the same answer, get the same polynomial from this calculation. Okay, so it's conjectured that the unknot is the only knot for which the Jones polynomial is 1. It's still conjectural. It hasn't been proved. In fact, the complexity of this problem is unknown. There's been work that suggests this might be polynomial time, whereas people thought maybe a few decades ago this was an NP problem. So it's a lot of these questions that are very, very basic about these polynomial invariants are still unanswered, or at least not formally proved. The Jones polynomial associated to this figure 8 knot, this knot with 4 crossings, is this object here. So it's got degrees that are both negative and positive. So it's some polynomial. Okay, so the knots that are in boxes, these are called hyperbolic knots. With these hyperbolic knots, I told you initially the knot's a circle embedded in a 3-sphere. Suppose I draw a little tube around the knot in this embedding and subtract out this tube and look at what's left over, the complement of this epsilon tube that I drew around the knot. That complement has a volume, and the volume of that complement is also a knot invariant for these so-called hyperbolic knots. So for these knots, we have another invariant, this volume, and what I'll do is try to see how these two invariants I've mentioned, the Jones polynomial and this volume, are related to each other. And I'll tease out the relation using machine learning. So that's how deep learning fits into the story as well. Okay, so up to 16 crossings, it turns out there are 1.7 million knots. And of these 1.7 million knots, only 32 are not hyperbolic. So nearly all of these knots are hyperbolic. And you can make a conjecture maybe, as a crossing number becomes very, very large, so going beyond 16 crossings to say 100 crossings, you can imagine the proportion of hyperbolic knots approaches 1 as the crossing number goes to infinity. This conjecture was made by Adams, and it turns out to be false. It contradicts another conjecture that the crossing number of a composite knot is not less than that of each of its factors. And in fact, there's now a theorem that says that as the crossing number goes to infinity, the proportion of these hyperbolic knots is strictly less than unity. So we need to be careful here in that we have this data set. In this data set, almost all knots are hyperbolic, and we can draw some conclusions using machine learning from this data set. But we should be wary about generalizing, because it turns out that the properties of the total set of knots may not be the same as we may be led to believe just by looking at small numbers of knots in our data set. So 1.7 million here seems like a large number, but in fact, we should be careful, even with numbers of this magnitude. Okay, so there was this relation that connected the color Jones polynomial with the volume. So the color is represented by this index n. This index represents the size of the matrix we're using in order to do these calculations. So in the limit, working with infinity by infinity matrices, then the claim is if you take this color Jones polynomial, the one you evaluate with this infinity by infinity matrix, and you evaluate this polynomial at a particular root of unity, then this calculation on the left-hand side will recover the volume of the complement of these hyperbolic knots. So this is a conjecture. There's been various circumstantial evidence to support this conjecture. If you take a particular knot, which is considered to be a rather simple knot with 18 crossings, it's simple in the sense its volume can be computed very easily. We find the convergence to the prediction, the right-hand side, as a function of n is rather slow, and in fact it's not monotonic. It goes up before it goes down and to converge to the right value. So the expectation based on this one knot where you can do all of these calculations is that maybe this is true, the n goes to infinity limit, but by looking at small n, you shouldn't expect it to be true generically. Okay, so that's maybe the expectation you have based on one of the few knots which you can calculate these Jones polynomials for arbitrary color. Let me not go into these details, but let me just say that we have presented a number of characters, and these characters, there's a famous absurdist play by Luigi Pirandello, 6 characters in search of an author, and I'm going to propose that the author which connects all of these characters are presented is a neural network. So the neural network, which you have heard of in, no doubt, in numerous contexts already, is an old idea. It was developed by Rosenblatt in the 1950s. He was working at the Cornell Aeronautics Laboratory in his Associated Naval Research Lab, and he noticed that if you take an input vector and you weight the different entries in your vector with these different weights, and you add a nonlinearity, you're able to make a prediction for some quantity based on these inputs with some accuracy. So this nonlinearity can be some logistic sigmoid function, which looks like this. It could be a ramp function. It could be a tangent function. We lots of different functions that roughly shape the same way. They go from 0 to 1 in some hopefully smooth way, but it needn't be smooth. In fact, this is sort of the preferred architecture that's often used today. This function, which is 0 for negative values, and just the slope, just the value for positive values. Okay, so if you put these perceptrons together, and you, instead of having just one weight, you associate a matrix worth of weights by passing this input vector into a different set of objects, these neurons, then you can construct this feed-forward neural network, and you essentially have some at each layer of the neuron, you're mapping the data associated to this vector to this vector. There's a map from one vector space to another vector space to which you associate this nonlinearity in a way. And then what you do is you present your network in training with examples of vectors and answers. And then you try to tune these weights and these so-called biases in order to make a prediction on inputs where you don't tell the neural network what the answer is, and you see how well it performs. So the idea is that we have this map between vector spaces at each set of pair of layers, and we take this matrix, this weight matrix, and we rotate this vector by acting with this weight matrix. We may add some bias that also introduces linear shift, and then afterwards we take this new vector we obtain and we act with this nonlinearity, and then we iterate this process through multiple layers, and then we compare the prediction to what's called the ground truth for the situation for which we know the answer in training, and then we try to determine what these elements in this weight matrix, these bias vectors are, and then we, in the training process, we minimize a loss. It might be the mean squared loss, and then after training, we apply this to unseen data and see how well we do. So in the case of these knots, I want to associate one invariant to another invariant. I've got this polynomial invariant, and I've got this volume. I want to see how these things are connected. So the polynomials, they're described by the minimum degree, so the minimum power in the polynomial, and the maximum power in the polynomial, and all the coefficients. So the these are represented as an integer vector, and for the knots up to 16 crossings, they're at most 18 vectors. So I take this simple neural network composed of 2 layers. So I've got 12,000 parameters that I can tune, the bias vectors and the weight matrices associated going to the input to this first layer, and then going from the first layer to the second layer, and the output layer is just a sum of whatever is produced. So I get a total of 12,000 parameters, and I use the nonlinearity associated to the sigmoid. I can choose another nonlinearity and get essentially the same answer. And I train on some fraction of my knots, and I test on the remainder of the knots to see how well this trained neural network performs. When I do this experiment, I train on 10% of 313,000 knots up to 15 crossings. I find that I predict the volume on the unseen data with an error of about 2.5%. So I do reasonably well in making a prediction based on training with a very small data set compared to the total data set of knots. So typically, these experiments you do in machine learning, you report the test set to be 80% of the data. You suppose the training set to be 80% of the data, the test set to be 20% of the data in these canonical experiments that you often see reported in literature. So here, even with a tiny fraction of the data, you're able to get good predictions. So this suggests there's some deep connection that explains why this is going on. Why are these two invariants, knots, so intimately related to each other? So these experiments I did in Mathematica initially. So the important code is in yellow. It's basically 2 lines of Mathematica. So these are the kind of experiments you can easily do with the data sets you encounter. And this is the calculation of this code in real time on 10% of the data set associated to these knots. And we see that the error in training is decreasing. So it's learning something in this process. And after it has gone through the training set, we'll see how it performs on the test set. And again, this is a real-time calculation on an older model laptop, so it's even faster these days. And we find that we obtained the plot that I showed earlier momentarily. So again, these are kind of experiments you can do very easily. So if you have large spreadsheets, machine learning is a good way to associate the columns of the spreadsheet to each other to see what correlations there are in these data sets. Okay, so we found that some function of the Jones polynomial expressed by the neural network gives me the volume, but it doesn't give me the volume on the nose. There may be some small corrections that explain this 2.5% error. In fact, it turns out that the Jones polynomial doesn't uniquely identify the knots in my data set. So you can have 2 different knots with the same Jones polynomial, but different volumes. When that happens, the difference in the volumes is about 3%. So the neural network is doing as well as can be expected on this data, because the data set is not such that there's a 1-to-1 correlation between volume and Jones polynomial. And the same applies to these 1.7 million knots with 16 crossings. I just haven't shown you that. It takes a bit longer to run. So there's a theorem in computer science called the universal approximation theorem. It says that the neural network with the sigmoid activation I've been using, and 1 hidden layer rather than the 2 hidden layers I've been using in these experiments, but even with 1 hidden layer and a finite number of neurons in this layer, you can approximate a continuous function that's suitably well behaved on compact subsets of some real vector space arbitrary precision. Now, the surprise here is that this theorem only says we have a finite number of neurons. Finite could be huge, but it turns out that a very simple architecture does the job of prediction really well. We want to see whether we can translate this observation, the neural network predicts the volume from the Jones polynomial, to an analytic result, something which is not machine learning. So we seek to reverse engineer the neural network to obtain some analytic expression for the volume. And we want to interpret this in terms of physics, because these polynomials, they arise from these quantum field theories. Okay, so when we were studying this problem, my student, Jessica Craven, discovered this idea of layer-wise relevance propagation in literature. The idea is basically take your neural network, and for each neuron in each layer, you assign a relevance score. This explains how important this particular feature is in calculating the final answer. And there's some prescription for assigning the relevance for each of these neurons. And as well, you apply a relevance score for each of these inputs. We found that if you take these different knots, and this time instead of feeding it the polynomial in terms of its coefficients and degrees, we're feeding the neural network evaluations of the polynomial at different complex phases. If we feed these data to the neural network, we find the same features light up. Each of these columns represents a different knot, and we see that the same features, the important features, are in red. The same rows are in red each time. So that's the feature with the highest relevance score. This set of experiments basically told us that certain evaluations of these Jones polynomials at these phases, at these particular primitive roots of unity, are able to predict the volume. And that's the only significant input the network uses in making its prediction, because those are the ones with the large relevances. Everything else is a small relevance in comparison. So we found that there's a particular phase, either the 3 pi I over 4, that does the best. All these other phases, they do much worse. And in particular, if you pick a very bad phase, you get an error of about 12%. The error in 12% is just the latent error in the data set. If you take all the knots you have, you assign to every knot the average volume of all the knots in the data set, that'll give you a 12% error. So this phase, which gives us a 2% error, does much, much better. And this phase itself is enough to predict the volume just by evaluating the Jones polynomial at that phase. And based on this evaluation, we're able to come up with some analytic function that does nearly as well as a neural network. And this behavior we can explain in terms of Chern-Simons theory, the quantum field theory that enabled us to determine the Jones polynomial of the knot to begin with, at least in principle. So the lesson from our investigation is the approximation formula works well when an object called the geometric conjugate connection makes a contribution to what's called the Chern-Simons path interval. That's just a fancy physics way of saying that there are particular phases that matter and certain phases don't matter so much. And we can sort of explain this in terms of an extended version of this Chern-Simons theory that we obtained from a process called analytic continuation. So there's a physics explanation for this phenomenology we've noticed that this phase tells us something about the knot. We've done this for what's called the fundamental representation Jones polynomial. These are the ones you obtain from these 2x2 matrices. If we use 3x3 matrices, we can repeat the same experiment. With 3x3 matrices, there was no existing database of these Jones polynomials. We had to generate this database. Once we generated a database, we found there's again a phase that does really well. And we can fit this phase that does really well with these 3x3 polynomials. Now, for these 4x4 and 5x5 and so on, we don't know what these polynomials are. But based on these two data points, we can make a guess for which phase to use. And we have this guess here that we will check eventually by generating new data sets to see how well the same experiments perform with this extended data set. So we're able to make some predictions about these colored polynomials, and we can see how this convergence happens to this volume conjecture that I started out with. In this n goes to infinity limit, we're working with infinity by infinity matrices. And if we take particular knots, we see that our guess, this knot's a figure 8 knot. This is one of these knots which can compute all these colored Jones polynomials. We see that our guess is in orange, and it does better than the naive expression predicted with the volume conjecture. The green is the actual answer, so the convergence is still pretty slow. In fact, you can see it's not monotonic here either. So we haven't come up with the best version of the volume conjecture, maybe. Everything's a smooth convergence that happens very quickly. And this is a knot, the 18 crossing knot I talked about earlier. We find that our guess works better than the old guess. So we're able to improve on aspects of this volume conjecture in knot theory. So knots are one of these objects for which there's a lot of data. Mathematicians have tabulated lots of topological invariants that go beyond the Jones polynomial and the volume that I've discussed. And there's this Nature paper that looked at looking at various these knot invariants. They used what's called saliency analysis, and they were able to find relations between different topological invariants, and eventually they proved a theorem that they associated with these invariants. Knot theory is also an area which is active in the sense that a lot of people are working on these ideas, and there are a bunch of papers that try to use machine learning to understand the aspects of these topological invariants of knots. So where are we headed with this? One of the famous statements in mathematics is called the Poincare conjecture. The Poincare conjecture is actually a series of conjectures, and most of these conjectures, when they're proved, they win someone a Fields Medal, the top prize in mathematics. So it turns out that the most recent progress in this was the Poincare conjecture for 3 spheres, which Perelman famously proved and declined the Fields Medal for, and also the Clay Prize for. The case where we're talking about 4 spheres, the answer is not known, and the reason that knots are important in discussion of the Poincare conjecture, which basically defines what a sphere is for 4 spheres, is that certain knots, if they have certain topological invariants, they provide counterexamples of the Poincare conjecture. So by studying these topological invariants and seeing how they're associated, you may identify candidate counterexamples. This important statement in mathematics. And this is something which we're actively studying. We can use neural networks to make predictions about the smooth Poincare conjecture in 4 dimensions. I'll be happy to tell you more about that if there are any questions, but I don't want to get into the details here. This is an important unsolved problem in mathematics that is related to knots, and these new technologies relating knot invariants to each other using machine learning can identify knots to study in order to see whether they're counterexamples. Okay, so that's my knot theory bit. Now I'll talk about another application of machine learning topology, and this involves what are called Calabi-Yau manifolds. These are the manifolds that arise in string theory to explain how you go from 10 dimensions down to 4 dimensions. So Francesco asked initially, how did I get involved in this, and what's the connection between particle physics and all these things, and cosmology and string theory? Well, this is it. So the idea is that we have a theory of forces of nature. One of these forces is gravity. Gravity is described by the geometry of space-time as expressed by the Einstein equation. The left-hand side of the Einstein equation is about geometry. The right-hand side of the Einstein equation is about matter, and it turns out these are related. The famous realization of Einstein is the presence of matter and energy tells space-time how to curve, and similarly, the curvature of space-time tells matter how to move. That's how the left-hand side and the right-hand side enter into description of space-time. In addition, we have a standard model of particle physics. It explains how particles interact. And this is a quantum field theory. It's called the Standard Model. It's the best tested theory in the history of science. So you do an experiment, and you make a theoretical calculation. Is agreed at 13 decimal places. There's nothing else like it. Even the 1 over r squared force law you learned about when you're talking about Newtonian forces, that, or Coulomb forces, that 2 in the 1 over r squared has not been measured at 13 decimal places. This is it. This is the most detailed agreement between theory and experiment anywhere. So it's a well-tested theory. It's our best tested theory in science. Now, we want to put quantum field theory and general relativity on an equal footing. Turns out that there's a problem when you try to do this. Non-gravitational interactions are not encoded as geometry the way gravity is encoded as geometry. There's a theorem in quantum field theory that says you can't do this. But there's a loophole in this theorem. Loophole is you can express these forces that we encounter in the standard model in terms of higher dimensional geometry. So the simplest example of this is what's called Kaluza-Klein theory. It's a unified theory, the first unified theory, which explains how gravity fits together electromagnetism. And instead of thinking about a four-dimensional space-time, think about a four-dimensional space-time with a tiny circle on top. The symmetry of the circle is a group. It's called U1. It's a group of phases. And as it's a phase, is a circle in the complex plane. And that circle is this extra dimension you introduce. So the symmetry associated with electromagnetism is realized geometrically as this circle, this fifth dimension. So we can apply the same idea to higher dimensions. So string theory tells us there are 10 dimensions. We see 4 dimensions. We see 3 dimensions that are spatial plus time. And we can go from 10 to 4 by thinking about 6 extra small dimensions. These dimensions are small because we haven't seen them before. We don't have a microscope which is powerful enough to resolve these dimensions. But in order to reconcile this quantum gravity theory, which allows us to unify gravitation with the other forces in nature in principle, we can have a 10-dimensional theory that gives us 4-dimensional physics by having 6 dimensions being really small. And for technical reasons, we're looking at geometries called Calabi-Yau spaces. These Calabi-Yau spaces have the property that when you compactify these 10-dimensional theories on these spaces, you get what's called an n equals 1 theory in 4 dimensions. What n equals 1 means is there's a supersymmetry in the game. The supersymmetry says that fermions and bosons come paired. So fermions and bosons are the particles we encounter in nature. They tell us about the statistics of these particles. Electron, for example, is a spin 1/2 particle. It's a fermion. The photon, for example, is a spin 1 particle. It's a boson. So half integer spin are fermions, integer spin are bosons, and supersymmetry says that for every integer spin particle in nature, there's a fermionic counterpartner, and vice versa. This is a technical simplification, but it has not been seen experimentally, so it's really a theoretical thing. And this theoretical thing allows us to answer certain puzzles that exist within the standard model. For example, why is the Higgs mass so small? So the boson and the fermion come paired, and that's what supersymmetry means. It explains why the Higgs mass is small compared to the fundamental scale of the theory, but so far we don't see evidence for this in our experiments in laboratories like CERN. Now, the simplest analog of this Calabi-Yau space, the 6-dimensional extra space that I'm tacking on to the 3 + 1 dimensions that I see, is a manifold, a geometry, the same family as the 6-dimensional Calabi-Yau, but it's a 2-dimensional torus. In this case of the torus, there is this hole, and this hole characterizes topological invariant of the space, as we talked about at the very beginning. Now, in order to characterize a torus in general, you need 2 parameters. One tells us the size of the torus, the area, and the other tells us the shape of the torus. So if you consider some old school video game, you think about boundary conditions that you put on the edges, and a particle that goes through this boundary comes out of this boundary. So the fundamental domain is this parallelogram in the complex plane. Now, the angle here tells us about the shape of the torus, because it needn't necessarily be a rectangle or a square. It could just be some arbitrary parallelogram with this parameter. So the torus is characterized by these two parameters, one a size parameter, one a shape parameter. These Calabi-Yau spaces are similarly characterized by size and shape parameters, and they're constructed in various ways. One of the ways is by starting off with a reflexive polytope. Let me tell you what a reflexive polytope is. So consider some shape. Let's start with two-dimensional polytopes. Let's consider shapes in the plane such that the vertices of these shapes are at integer points on the grid. So, for example, the triangle 0, 1, 1, 0, -1, -1 is an integer lattice triangle. It's called reflexive because there's a single interior point which takes to the origin. Another such polytope is the square, where the vertices are at 0, 1, 1, 0, 0, -1, -1, 0. And again, there's a single interior point, the origin. All of these lines that I'm drawing that define the polytope are at unit distance from the origin. So the line, for example, x plus y equals 1 is one of these edges. And the x minus 2y equals 1 is another one of these edges. All of these right-hand sides are 1. So a unit distance from the origin. So this condition that all the edges are at unit distance and there's a single interior point defines this reflexive polytope. You can consider all the possible shapes that have this property, that the edges are at unit distance from the origin and there's a single interior point. It turns out that there are 16 such shapes that satisfy this condition, and these are the 16 shapes. So we can do this in 2 dimensions without any difficulty. In 3 dimensions, we can also do this, but it's more difficult. And in 4 dimensions, we can again do this, but it's even more difficult. And in 5 dimensions, we don't know the answer. So in 2 dimensions, there are 16 such geometries. In 3 dimensions, there are 4,319. In 4 dimensions, there are about 500 million. And in 5 dimensions, the best guess anyone has is 10 to the 18. So we have no idea what the answer is. So it turns out there's a prescription to start from a polytope and build one of these Calabi-Yaus. So if you start from a 4-dimensional polytope, you'll end up with these 3-dimensional, 3 complex dimensional, or 6 real dimensional Calabi-Yaus I talked about previously. These 4-dimensional Calabi-Yaus, or 8 real dimensional Calabi-Yaus, they arise in certain string theory models. So we're interested in knowing something about the polytopes that exist in 5 dimensions. We can use machine learning, use genetic algorithms to emulate Darwinian evolution in order to solve for these things. So we think about some population, and these populations are characterized by zeros and ones, which I've colored green and red. And we can think about each of these polytopes as being represented by the genes. Each of these bits represent the data about a polytope. And we can rank each of these polytopes by how close they are to being reflexive, how close they are to having their edges to be unit distance from the origin, and how close they are to having only a single interior point. Then we apply the usual rules of Darwinian evolution. We use selection and crossover to indicate breeding between elements of this population I've got. And then we can also introduce mutation by randomly changing a 0 to a 1, or a green to a red, or vice versa. And we can apply this in order to characterize these polynomials. We have some fitness function that tells us how close we are to satisfying the properties of reflexivity I talked about previously. So again, the details don't matter. I'm just trying to generate polytopes that have properties that I want. And I can do this using machine learning. And I succeed in finding new examples of these polytopes in 5 dimensions. So these are the vertices that are all integer points. And if you draw this in 5 dimensions, you can notice that there's a single interior point, the origin. So we construct new polytopes in this way. And they have some nice physical properties that are corresponding to phenomenology we might be interested in particle physics model building. Okay, so I've shown you 2 examples of using machine learning, or the tools associated to machine learning, to study topology of objects. The first set of examples was relating topological invariants of these knots, and these were connected deeply to quantum field theories. The second set of examples was in finding certain polytopes with properties I found interesting, because these properties turned out to generate these Calabi-Yau spaces, which are important for these string constructions of particle physics. So we start from string theory, we go down to 4 dimensions by using these Calabi-Yau spaces, and these methods of machine learning enable me to find new Calabi-Yau spaces of interest when I do this. So where are we headed? Well, in the progress of mathematics, computers were a relatively recent innovation. So computers played a role in solving 2 important problems, which convinced mathematicians of their importance. The first such problem was the classification of finite simple groups. The periodic table of groups with a finite number of elements. It turned out that there were some exceptional groups, these so-called sporadic groups, and these tables, which tell us how to multiply group elements and characterize these group elements, required use of computers. So this was one important innovation that demonstrated the utility of computers for doing advanced mathematics. The second development of this type was solving the 4-color theorem. So if you take any map, it turns out you can color such a map using only 4 colors, so that no 2 states or provinces have the same color when they abut each other. And this is proved by Appel and Haken, essentially by exhaustion, by drawing all the possible maps you can have using computers. So this was another example of how computers found a home in mathematics. So far, machine learning has not been able to do the same thing, in the sense that there hasn't been a similarly deep result which required machine learning in the same way that these deep results, the classification of finite simple groups and how to color graphs, required computers. So we're in search of such a use case where these machine learning insights lead us to really, really important theorems, rather than the sort of important theorems we saw, for example, in that DeepMind paper that made Nature. So we have reason to believe this is a reasonable goal to shoot for. We have these machine learning algorithms where you have a black box that's somehow learning a language without knowing the details of the grammar of the language. We have the example of Go and chess, in which in Go, for example, computers are able to find innovative new opening sequences. In chess, for example, there are no new openings per se, but the middle game and the end game have been innovated by using these deep learning methods. So in some sense, there are examples, there are indications that computers can be creative in the setting of formal games like chess and Go, but also mathematics. And then there are things that are being developed. These proof assistants, Lean in particular, is being used by fields medalists these days to check their proofs. So there's a structure in which you can automate theorem checking. But there's also the ability of computers to write proofs in real analysis, the level of a graduate course that a professional mathematician can't distinguish from a graduate student written proof. So mathematics is being done by computers at some elementary level, at least. So you want to put all these pieces together. You have logical reasoning. We now have large language models that write mathematics fluently, and then we have these creative computers in certain restricted contexts like Go and chess. So if you put all these pieces together, maybe you can have a silicon mathematician. And then we have to confront the issue of how do you collaborate effectively with our silicon colleagues. So that's something which we should think about because I think this is the future. So thank you.
Yeah, thank you very much, Vishnu, for an excellent talk. Are there questions? Any mathematicians that want to complain about the future of mathematics? Let's start with the mathematician here. Donovan, thank you.
Thank you very much. Definitely nothing to complain for, and thank you for the presentation. It was a nice presentation. Two questions. In the first part of your talk, I think I missed, at some point you said that you were trying to extract a formula for counting that the difference factor. And then I missed if you showed us the formula or not.
It's written on top there. If I evaluate this Jones
see.
polynomial at this particular phase, I plug into that formula, I get 3% error roughly, which is comparable to the neural network.
Yeah, so that formula was extracted from the neural network, right?
The neural network told me which phase to look at, and I just looked at that phase and just did a best fit.
I see. Thank you. And then the other question is, if you're familiar with the most recent research on DeepSeek Prover version 2, it's about advancing formal mathematical reinforcement learning for subcode decomposition. I think it fits into your...
It does. I mean, I don't know the details of DeepSeek in particular, but all of these efforts to formalize games uses this reinforcement learning idea. So Go and chess.
Yeah, so this
solve
project is specifically about now incorporating that creative aspect
Yes.
of machine learning into proving theorems.
Yes, because in some sense, if you have some axiomatic structure in mathematics, it's also defining the rules of the game.
Yeah, exactly.
And then
Yeah.
you're trying to apply the same idea. Yes.
Yeah, so there is a recent article on Archive.
Okay.
Please, Martin. The phone is on the way.
Yeah, thank you for a very nice talk. I have a question. I mean, at the beginning, you mentioned that there are these huge databases of knots.
Yes.
You also mentioned that there was sort of a mistake with uncrossings, that one knot was repeated. I was wondering how these databases are constructed, and is there a sort of computer program that one can write that would, just enumerate all the possible knots, as many as you want, or how that all works?
Right. So this has sort of been done up to a small number of crossings. So it gets very complicated very quickly. The number of knots grows very, very, very fast, the crossing number, which is sort of a proxy for complexity for a knot. So up to, I think, 19 crossings, these databases do exist. Beyond that, there isn't a complete database. And the knots in the database are distinct because there's some topological invariant which distinguishes any pair of knots from each other in this database. So there's a belief that the kind of accidental mistake that happened isn't repeated in the current databases. But that's there's some topological invariant that differs between any pair of knots in the database. These databases are complete in the sense that up to this number of crossings, we've drawn all the possible combinatorial arrangements of the different strands we have. This is sort of done by exhaustion, and then these are checked up to equivalency, so-called Reidemeister moods I mentioned. But in general, we don't have complete databases beyond some finite number of crossings, a small number of crossings.
So if you would want to, say, extend that table, is some new idea needed, or is it just a matter of computer time? Or
I think computer
what
power is the most
what
important
is
thing
the
here.
obstacle?
I think it's computer power is the most important thing. But in general, you may want to come up with some way to randomly sampling knots at a high number of crossings, because we expect that, say at 100 crossings, there's just too many knots to write down the complete database of knots at that number of crossings. So you want to come up with some way of fairly sampling these and then studying that sample. We don't have a good algorithm for randomly selecting knots at a high number of crossings. There are various proposed models with their own strengths and weaknesses, but I don't think anyone agrees upon a consensus model for how to randomly select knots at high crossings.
Okay, thanks.
Is a question at the back, Mesias, please?
Thank you very much again for the nice talk. I am just curious to know if there's a link between the approximation theorem the universal approximation theorem, and the bias stress approximation theorem.
I don't know offhand.
That it says that every continuous function on a compact interval, 0 and 1, can be approximated by a sequence of polynomial.
I think there is some moral relation. I don't know the details, but it wouldn't surprise me if these two were related. The universal approximation theorem applies to things beyond an interval. It applies to compact subsets of Rn. But morally, these sound like similar statements. But the universal approximation theorem is about neural networks, which are nonlinear things, right? So it's not really exactly the same as polynomial comparisons.
Any other questions or other questions from our online participants? No? Then here, there's a question here in front. Donovan, you will do your 10,000 steps today. Please.
Is there any known topological way to determine if a knot is stronger than another? Better for...
I mean, I'm not sure there's what do you mean by stronger or better? I mean,
I don't know that it's better to use that to anchor your ship to...
I think for purposes of anchoring a ship, I think simple knots are probably enough. I don't think we need to go through 20 crossing knots to do this job. But yeah, I mean, I'm not sure about the strain and stress and so on for a knot. That's too practical for me.
Okay, then if there are no more questions, Vishnu, thank you very much
you.
again. And as a little thank you,
Oh.
copy of our famous Bizarre magazine. Yeah, you might have seen it online, but
Thank you very much.